Welcome to this first video of a playlist about the chemistry of carbon dioxide. These 5 new videos replace an older playlist. As usual, you can find a PDF version of the slides under the Community tab of my channel. In this first video, we'll have a look at the distribution of carbon dioxide, about its current sources and sinks, about the changes of its concentration in the atmosphere over time, and its impact on the Earth's climate. In the second video, I compare the reactivity of carbon dioxide with that of methyl isocyanate and ketene, and explain the reasons for the huge differences between these 3 compounds. The third video is about carboxylations at carbon for the synthesis of carboxylic acids, including carbonylations with carbon monoxide. Part 4 is about carboxylations at nitrogen and oxygen, and in part 5 we'll have a look at the decarboxylation of carboxylic acids. But first some words about the oxidation states of carbon. Just like chemistry is sometimes called the central science, halfway between physics and biology, carbon is the central element, halfway in the second period and far away from its closest noble gases, helium and neon. Because of this central position in the periodic table, it would take the addition or removal of 4 electrons from a carbon atom to reach the electron configuration of a noble gas. That's just too many electrons, and instead carbon forms not ionic but strong covalent bonds with itself and with most other elements, giving rise to the extremely rich and varied chemistry of carbon, the so-called organic chemistry. Around 150 million compounds containing carbon have been described in the chemical literature, and many more are conceivable, while less than 1 million compounds are known that do not contain carbon. To better understand the energetics and reactivity of organic compounds, we can assign formal oxidation states to carbon. Whenever carbon forms a bond to an atom with significantly higher electronegativity than carbon, the formal oxidation state of carbon would increase by 1, even if the bond is not ionic but covalent. This would include bonds to nitrogen, oxygen, or to the halogens. And when carbon forms a bond with an element of similar electronegativity as carbon, the oxidation state would remain unchanged. Hydrogen has, according to Pauling, an electronegativity of 2.2, slightly lower than carbon. Thus, in simple alkanes and in elemental carbon, the formal oxidation state would be 0. I've sketched here compounds with only 1 carbon atom and their formal oxidation state. Carbon in alcohols like methanol would be oxidized once. In ketones or aldehydes like formaldehyde, it would be oxidized twice. In carbon monoxide or carboxylic acids like formic acid, it would be oxidized 3 times. And in carbon dioxide and carbonates, including all the inorganic salts of carbonic acid, it would be oxidized 4 times. If we compare the heats of combustion of these compounds, that is, the energy released during complete oxidation to water and carbon dioxide, we see that the energy content drops with the number of carbon-hydrogen bonds and as the oxidation state increases. Thus, alkanes yield more energy than alcohols, which in turn are more energetic than aldehydes or carboxylic acids. Carbon-carbon bonds like those in graphite or diamond yield less energy upon oxidation than carbon-hydrogen bonds. Reactions where the oxidation state of carbon remains unchanged do not usually involve such huge energy differences. The hydration of formaldehyde, for instance, only yields about 30 kJ per mole, while the hydration of carbon dioxide is endothermic by 2.2 kJ per mole. This is also true for reactions like the formation of imines or enamines from ketones, or the transformation of various carboxylic acid derivatives, for instance saponification, esterification, or the formation of amides from acids. The formal oxidation state of carbon remains unchanged in these reactions. As a rule of thumb, reactions that cause a change in the oxidation state of carbon require more energetic reagents and tend to proceed less cleanly and in lower yield than reactions where the oxidation state of carbon remains the same. Thus, to reduce carbon dioxide or inorganic carbonates to carbohydrates or to alkanes, we'll need a lot of energy, and some of this energy will be released again if we burn these carbohydrates. The reduction of carbon dioxide by photosynthesis has been going on for many years, first by cyanobacteria and later by plants. With sunlight as energy source, carbon dioxide was reduced to carbohydrates and water was oxidized to oxygen. These carbohydrates, mostly cellulose, were buried and slowly converted into coal, crude oil, natural gas, graphite, diamonds, and carbon dioxide by disproportionation. So, some of the carbohydrates were oxidized by other carbohydrates to carbon dioxide, while the latter were reduced to alkanes and elemental carbon. It is important to understand that photosynthesis is the only natural process by which oxygen is formed. All the oxygen in the atmosphere, currently about 21%, was formed by photosynthesis. As a child, I was very concerned about this because I assumed, correctly, that if we go on burning fossil carbon, oxygen levels would drop to zero and we would all die of suffocation. We would actually die much earlier because carbon dioxide already becomes lethal at concentrations of 5 to 10%. But relax, this will not happen. Because all the oxygen in the atmosphere was formed by photosynthetic reduction of carbon dioxide, we know exactly how much reduced carbon has been buried over the years. This is about 450 times more than our current best estimates of remaining fossil carbon deposits. Most fossil reduced carbon formed by photosynthesis is not recoverable, either because it is too dilute or because it has disappeared into the Earth's mantle and core by tectonic subduction. The core of the Earth is mostly elemental iron and nickel and can dissolve a lot of reduced carbon. Actually, 80 to 90% of the Earth's carbon is in its core. Only a tiny fraction of the reduced fossil carbon remains in sufficiently concentrated deposits in the Earth's crust to be recoverable. And if we burn all the remaining oil, coal and natural gas, oxygen levels in the atmosphere would remain almost unchanged. This graph shows the partial oxygen pressure in the Earth's atmosphere over the last 4,000 million years. Currently, the atmosphere contains 21% of oxygen, most of which was formed during the last 1,000 million years, when plants began to cover the continents. The peak of oxygen concentration was about 350 million years ago, in the Carboniferous. It was caused by extensive forests of fast-growing but short-lived trees, which, upon dying, were buried and later converted into coal. Such trees no longer exist today, and our current rainforests do not capture carbon dioxide as quickly as they did in the Carboniferous. Carbon dioxide levels at that time dropped to as low as 150 ppm, causing glaciation of the poles and the extinction of many animals and plants. But much worse was to come. Around 250 million years ago, at the end of the Permian period, the largest volcano ever erupted in Siberia, in an area with oil and coal deposits and a lot of calcium carbonate. This caused the emission of huge amounts of methane, carbon dioxide and sulfur dioxide, and a strong heating of the climate and acidification of the oceans. About 70% of all species of plants and animals faced extinction within a few thousand years. Methane is a powerful greenhouse gas, but its half-life in the atmosphere is only 10 years. The oxidation of methane consumes oxygen and generates carbon dioxide, and this oxidation of reduced carbon and the disappearance of the rainforests of the Carboniferous were the main reasons for the drop of oxygen levels and a renewed increase of carbon dioxide levels to around 2000 ppm. These were the CO2 levels during the Permian, Triassic and Jurassic period, when the dinosaurs ruled a much warmer planet. This slide shows the current approximate carbon distribution on the Earth's surface and crust. Most carbon is not reduced, but at oxidation state 4, in the form of inorganic carbonates and bicarbonates. Around 7% of the Earth's crust is calcium carbonate, 26,000 times more than the bicarbonate dissolved in the oceans. Of the total amount of carbon in the oceans, the atmosphere, the biosphere, and in the estimated recoverable deposits of reduced carbon, the atmosphere contains about 2%, the biosphere about 5%, and the fossil deposits about 2% of carbon. Most of the carbon in the biosphere is in plants and microorganisms, while animals account for less than 0.5% of biosphere carbon. So, if we burned all the recoverable fossil carbon so fast that the CO2 had no time to dissolve in the oceans, theoretically we would double the current atmospheric CO2 levels. As I'll show you later, however, higher temperatures also cause increased CO2 emissions from land and sea, and future CO2 levels are therefore difficult to predict accurately. I've sketched here the average global carbon budget for the years 2014 to 2023. The natural CO2 flux, that is the CO2 absorbed and released by microorganisms, plants and animals, is about 210 gigaton carbon per year, which is large compared to mankind's additional emissions. These, caused by the burning of fossil-reduced carbon and changed land use, amount to about 11 gigaton carbon per year. A large fraction of these emissions are absorbed by the oceans and the soil, while the excess CO2 slowly accumulates in the atmosphere. If we would stop burning fossil fuels right now, and if the ocean and terrestrial CO2 sinks would continue absorbing CO2 like they do now, it would take about 70 years to halve the current atmospheric CO2 concentration. But with so many ifs, such estimates are of course rough approximations only. Another important mechanism of carbon dioxide removal from the atmosphere is silicate weathering. This process is slow compared to those of the previous slide, but is critical for the long term. The Earth's interior is quite dynamic, and tectonic plates collide or break apart, as sketched here. Earth's crust and mantle consist mostly of aluminosilicates and contain only a small percentage of carbon. Fresh silicates emerge from the mantle to the Earth's surface, for instance when asteroids hit the Earth, when volcanoes erupt, or when tectonic plates separate. One typical silicate is wollastonite, but there are many more. Silicates are salts of silicic acid, and because silicic acid is a weak acid with a first pKa of 9.5, silicates are alkaline. Carbonic acid, with a first pKa of 6.5, is a stronger acid and will react with silicates to yield some form of silicic acid and inorganic bicarbonates. Silicic acid tends to eliminate water to form linear, two-dimensional or three-dimensional anhydrides, like silica gel and quartz. Thus, fresh silicates emerging from the Earth's mantle will convert gaseous or dissolved carbon dioxide into dissolved or solid inorganic bicarbonates. When silicic acid anhydrides and carbonates re-enter the Earth's mantle by tectonic subduction, quartz, lime, carbon dioxide and water will be formed, just like in a cement factory. Water and carbon dioxide will accumulate in magma chambers and be eventually released from volcanoes or hydrothermal vents, while quartz and lime are again transformed into silicates like wollastonite. Huge amounts of solid carbonates have also just piled up on the Earth's surface and in the crust. A few words on the chemistry of carbon dioxide in water. Opening a bottle of beer reveals carbon dioxide's limited solubility. This solubility drops with rising temperature, but increases strongly with the pH. At pH 7 to 10, carbonic acid will be deprotonated once to bicarbonate, and above pH 11, all the carbonic acid and bicarbonate will react to carbonate. Seawater has a pH of 8.2, and most ocean carbon is therefore bicarbonate. Currently, the concentration of carbon dioxide in the oceans reaches only 7% of saturation, and much more carbon dioxide can be dissolved. This takes time, however. If no bases are present, or if the bases are insoluble and hence unreactive, like silicates, then carbon dioxide will acidify seawater, what in turn accelerates the dissolution of silicates. Let's have a look at the historic CO2 concentrations in the atmosphere. This chart shows atmospheric CO2 for the last 800,000 years, as determined from Antarctic ice cores, and the temperature difference to our current temperature. The late anthropogenic increase of CO2 to about 420 ppm has been omitted. On this time scale, the climate oscillates periodically between our current, relatively warm period and much colder phases. These ice ages are caused by variations of the Earth's orbit around the Sun and changes in the tilt of the Earth's axis. Interestingly, the atmospheric CO2 concentration correlates with these temperature changes, probably because of the lower solubility of carbon dioxide in warm water. This chart covers a longer time than the previous chart. In the early Pliocene, 5.5 million years ago, the climate was quite different than today. Importantly, there were no periodic ice ages. These started around 2.5 million years ago and became ever more violent. The main cause for the onset of periodic ice ages was probably the drop in greenhouse gases, mainly carbon dioxide. With a drier and colder atmosphere, the climate became more sensitive to slight variations of the Earth's orbit and tilt. The recent severe ice ages were devastating events, with thick layers of ice covering most of northern Europe and America and exterminating plants and animals on a huge scale. This is the current best estimate of historic atmospheric CO2 levels and global mean surface temperatures over a still longer time, until the asteroid impact 66 million years ago, which wiped out most dinosaurs. The CO2 concentration is the upper blue curve with the left-hand logarithmic scale, while the global mean surface temperature below is in black with the right-hand scale. The two blue horizontal lines are the atmospheric CO2 levels in 2022 and the CO2 concentration below which most current plants would die of suffocation. Over the last 50 million years, there has been a steady decline of atmospheric carbon dioxide. This drop of CO2 levels probably caused the decline of temperatures. Cutting the CO2 concentration in half led to a 5-degree drop of the surface temperature, more or less. The main mechanisms of this decline of atmospheric CO2 must have been silicate weathering and photosynthesis, as discussed above. Emissions from volcanoes and hydrothermal vents have not been sufficient to maintain a constant level of greenhouse gases. Potential sources of fresh silicates could have been the formation of the Himalayas and the impact of asteroids, including the one which killed off the dinosaurs. Now, this chart bodes ill for the future of life on this planet. The pre-industrial CO2 levels were already close to the minimum required by current plants, and it is unclear if and how fast plants would be able to adapt to still lower CO2 concentrations. By burning fossil carbon, we'll only be able to maintain higher CO2 levels for a short time, and when the remaining carbon deposits are exhausted, CO2 levels will continue falling. Fortunately, we have now understood this potential problem. There is enough inorganic carbonate around, and in the future, with the aid of solar or nuclear power, we could increase CO2 emissions to maintain adequate greenhouse gas concentrations. Just as humans learned agriculture, in the long term we'll have to learn to control atmospheric CO2 levels, and thus the Earth's climate. So, what kind of climate should we expect with the current 400 ppm of carbon dioxide in the air? The fossil record paints a detailed picture of what the Earth looked like in the Miocene and how things changed between 23 and 5 million years ago, when the CO2 levels were in the range of 300 to 500 ppm. As the CO2 levels dropped during the late Miocene, the current Antarctic ice cap was formed and the climate became colder and drier. Tropical forests were replaced by savannas, grasses evolved, and many earlier species went extinct. In general, colder climates caused by a decline of greenhouse gases seem not to be particularly life-friendly. Lower temperatures lead to less precipitation, to the formation of deserts, to fewer species, and to a less productive biosphere. Even today, the areas with most species are in the tropics, not in the temperate zones, and life blossomed during the Permian, Triassic and Jurassic periods, around 200 million years ago, when CO2 levels were between 1000 and 2000 ppm, that is 2 to 5 times as high as today. Current CO2 concentrations are similarly high as between 25 and 5 million years ago. This corresponds to global mean surface temperature of about 3 to 5 Kelvin higher than today, once equilibrium has been reached. Right now, because of our extremely fast emissions, the Earth is imbalanced and it will take some time for the ice to melt and the oceans to warm up. However, the Miocene or Pliocene climate does not look too bad to me. The next ice age would probably be postponed if we could maintain the current CO2 levels. And the increased precipitation and temperature should reduce the size of tundra and deserts and improve the habitability of areas that are currently too cold or too dry for agriculture. Only the temperate and frigid zones would become warmer, while the tropics would more or less maintain the current climate. The only drawback is the rising sea level. But this will probably be a slow process, similar to the end of the last ice age 15,000 years ago, when the sea level rose about 120 meters within 10,000 years, at a speed of up to 3 meters per century. So nobody will drown, but I would rather not buy real estate close to the sea. Here are some more books if you want to dig deeper. There are also many good videos on the subject, for instance these 4 more recent ones. In the next video of this playlist, we'll have a closer look at the chemical reactivity of carbon dioxide, or its lack of reactivity, by comparing it to 2 closely related but much more reactive compounds, methyl isocyanate and ketene. So long.